Hi, so welcome back and let us continue our discussion regarding this topic here, which is the integrating factor. And once again, the rule of this integrating factor is that we need to find this out in order for a not exact equation to become a exact equation. Okay, so say we have this differential equation given we have x squared plus y squared plus 1 d of x is equal to negative x minus 2y d of y. Okay, so the first thing to do is, of course, you need to do some inspection if the other mentioned technique is applicable or not. And since we are in this topic, let's check and test if this is a exact equation. So by doing that, we need to of course determine our m and n, and before that we need to make our given equation into like this form. Okay, we have m xy dx plus n xy dy is equal to 0 in order for us to not easily find our m and n. Okay, so let's name this as our equation 1, and from equation 1 we only need to transpose this part here to the other side of our equation, making this part a positive. So we have square plus y squared plus 1 dx plus, okay, we make this positive since we will move this on the other side. So we have x minus 2y dy is equal to now 0. So as you can see here, we are now in this form. Okay, and by doing that, we can now simply determine where is our m and where is our n. So since this guy part here is multiplied by our d of x, so this is our m, and this part here is our n. Okay, or I'm just doing the shortcut, but you can also write the m is equal to x squared plus y squared plus 1, while our n is equal to just x times x minus 2y. Okay, so let's evaluate if this is truly a exact or non-exact equation by doing our test by having the partial derivative of m. Let me rewrite this on this part, m with respect to y, by making x a constant. So since this is a constant, because we are in partial derivative, so this is 0, so because the derivative of constant is just 0, as well as this constant 1 here. Okay, so we've only left with y squared, and the derivative of this y squared in terms of with respect to y is just 2y. Okay, and moving on the other side, we have to take the partial derivative of n with respect to x, making variable y constant. So this whole part here is constant. Okay, so we have wait. Okay, so since we have a derivative, I mean we need to you can simply distribute it first. You have x squared minus 2xy, then take the derivative, or you can just take the derivative of this form directly. Okay, so whatever you want. Okay, so having this, we have 2x and then minus 2y. So the derivative of this is the partial derivative of n with respect to x alone is just 2x minus 2y, okay, by making y constant. So as you can see here, partial derivative of m with respect to y is not clearly it is not equal to our n partial derivative of n with respect to x. So that means that our given differential equation here from equation 1, so yeah, let's call this also as our equation 2. Clearly that we after the evaluation, we say that our given differential equation, this part here, is not exact. Okay, so the next step is to find the integrating factor to make our equation 2 exact. Okay, so to find integrating factor. Okay, so we need to find the integrating factor. How? Just like what we have discussed last time, we have two conditions. In if we have computed that after we evaluated using that formula and come up with purely x alone, then we can now use the formula for that. And if our resulted value is purely y alone, then we can also use the other part. Okay, so let's check first by using this partial derivative of m with respect to y minus n with respect to x all over n is equal to, so what is our partial derivative of this part? Where is that part? So that is equal to 2y, so we need to substitute it in this. So we have 2y and then minus the partial derivative of n with respect to x, which is equal to this part here. So we have minus, okay, do not forget to make a bracket here, that because that whole term here is as minus to this term here. Okay, so we have minus 2x minus 2y, then all over our n is, where is our n? This part here. Our n, this part, so we have x minus 2y. Okay, and by doing that, let's simplify first. We have 2y, then distribute the negative sign. We have 2x minus, plus 2y all over x times x minus 2y. So doing it further, we can combine the y's here. So we have 2 plus 2, we have 4y, and then minus 2x all over x times x minus 2y here. So as you can see, we're trying to do some algebra here and find out if we can come up with a purely x function alone, or because this equation here is the test if we can get a purely function of x alone. Okay, so I'll be doing that. Since we have this, let's since we have as you can see here, we have 2y here and we have 4y minus 2x. So let's just try to factor out 2, having leaving us with 2y minus x, right? Then x times x minus 2y. Okay, so as you can see here, can we cancel this out? We have 2y, x and x, but if you notice, our 2y here is positive and our 2y here is negative, as well as our x here on the numerator is negative, while on and the denominator is a positive. Okay, so they nearly the same, but not quite the same because they are in opposite sign. So why just try to do some modifications furthermore in our algebra by factoring out a negative sign here. So if we do that, so we have negative 2, and then since we factor out a negative sign here, this will now become a negative 2y. So as you can see, from positive we now have a negative 2y, and since we factor out the negative sign, this part here now became a positive x. Okay, so if you want to check it, you can now distribute it negative 2 to this part here. Okay, so we have x minus 2y, and as you can see here, we've now already can cancel out in this whole term, the negative 2y plus x divided by this part here, because we both have negative 2y, and then positive x. Then, or maybe if you can wanna show that in a more easier form, then you can now interchange the position of 2y and x. So we have positive x, then negative 2y. Okay, so to just simply show that we can cancel this out. Okay, so we have negative 2, and then this part negative 2y plus x, and then all over x times x minus 2y. Then from here you can now clearly see that this part here can be cancelled out because they are equal to 1, and 1 multiplied by this is just negative 2 all over x, which is purely a function of x alone, because we cannot see any variable y there. Okay, so after this, so this is now our f of x. This is a purely function of x alone, negative 2 all over x. So if we if we have a purely function of x after evaluating this using this equation, our integrating factor now is, how can we find? Integrating factor is integral of f of x g of x, right? And it is now equal to integral of our f of x here is negative 2 all over x dx. Okay, then by getting the integral of this negative 2 over x, so we have a negative negative 2 ln of x, right? So we have negative 2 ln of x, and if we simplify it further, it only means that we have ln of, since we have negative 2 here, as the rule in our this kind of form, we need to make this negative 2 here the power of our x. So we have negative 2 yan, right there. Therefore, we can cancel out and ln. Thus, our integrating factor is equal to x negative 2, or just simply if you wanna make it on a fraction form, we have 1 over x squared.